Let's do reading assignment 4, section 4.1.1, problem 11. The question asks to verify the divergence theorem for the vector field given by z minus y, x, and negative x, and the region D given by the points x, y, z, where this expression is less than or equal to 1. So what we need to do is we need to show that the left-hand side of the divergence theorem and the right-hand side of the divergence theorem are the same. On the left-hand side, we have the flux. Actually, let me use black pen. On the left-hand side, we have the flux of the vector field through the boundary of the region D. The boundary of the region D means that instead of less than or equal, we have just the equality here. Now, in divergence theorem, we are not looking just for any flux, we're looking for outward flux. On the right-hand side of divergence theorem, we have the integral of the divergence of F over the volume D. So volume integral of divergence of F over the region D. Okay, let's first evaluate the left-hand side of divergence theorem. For this, we parameterize the surface of the region D. The parameterization is like this, shown here. You will notice that that this looks very similar to the parameterization for a sphere. The difference are these factors. So you see x is stretched by 2. The reason why is because this is an ellipse that's stretched by 2 in x direction, by 2 root 2 in the y direction, and by 2 root 3 in the z direction. That's why I'm choosing these factors here to represent that. And if you're not convinced, you can always go ahead and check that this parameterization is correct by just plugging in x, y, and z for all the expressions. Sorry, this bothers me. Yes. So let's check. I plugged in x here, y is plugged in right here. You see this expression. And then for z, I have this expression over here. Oh no, I made a mistake. Sorry. Okay. Here I have this expression. And then here's what we get. 2 squared is equal to 4, right? So then this cancels. 2 root 2 squared will give us what? Let's do it on the side. 2 root 2 squared is 4 from here times 2, right? So 8. So then this guy cancels. Here we get 2 root 3 squared, which is equal to 4 times 3. So we get 12. So this also cancels. From this, we get this expression over here, where this is sine u, and sine u is here, and it's squared. Then we have cosine squared v. We have sine squared u. This is what we got here. Sine squared v, and then here is cosine squared u, which is what we have here. Okay, then let's look at these two terms. Sine squared u is a common term, so this can be factored out of this sum, and we're left with cosine squared v plus sine squared v. And then we have plus cosine squared u. Now this part is equal to 1, right? So then we're left with sine squared u plus cosine squared u equals, which is also equal to 1. Now let's look at this. This is exactly what we're trying to show, that these x, y, and z lie on the boundary of this region D. So everything is fine. Our parameterization makes sense. Let's find vectors tu and tv. Remember, the tu is equal to the derivative of the position vector with respect to u. tv is the same thing but with respect to v. So here I'm showing parameterization. It's blocked. Okay, now you can see it. So here, let me just highlight the parts that got differentiated, and then the rest just stay the same. So you see, we were differentiating with respect to u, so only u, sine u ends up differentiated. The rest stays the same. Here we get cosine u. For this, same thing, everything stays the same except sine turns into cos. Here we get negative sine u. Let's consider this part. We have here only cosine gets differentiated. This is how I got negative and sine v, and then sine u stays the same. Here only this part gets differentiated. This is what I got here. Here nothing actually survives because nothing depends on v, so we just get 0. Next is to compute the cross product between tu and tv. So let's do this. So here I just copied everything exactly. Let me just check that it's correct. Yes, it's correct. Okay. So I copied tu over here and tv down below it. And then let's take the cross product. For x component, we get this cross product, which gives us 2. Oh, actually, hold on. I'm not gonna, oh no, what's happening? Sorry. So this part gives us 0, so we're actually only left with the second part, which is negative. So basically we get minus and then negative 2 root 3 times 2 root 2. And then we have sine u, so we get sine squared u and cosine v. For the y component, we get this determinant, and then I already included the negative, so we get this line with a 0 will give us 0, and this line will give us minus, and then this product, you see the two negatives cancel, so we're left with 2 times 2 is 4, square root of 3, square root of 3 times sine squared u times sine v. For the z component, we get the following. We get 4 square root of 2 sine u cosine u then we get cosine squared v. So this was this line. For this line, we get minus negative 2 times 2 is 4. Then we get square root of 2 sine u cosine u. And then we get sine squared v. On the next page, what I did is I just copied this exactly without any changes or simplifications. You can check that it's the same as before. So now let's simplify it. So you see there is this minus and minus, these cancel, and we get 2 times 2, 4, and then here we get 6, and then the rest is just copied. Here, negative and negative cancel, that's how I got this plus, and the rest I copied exactly. You can see it here. For the z component, you see there is this negative and negative, those cancel, that's how I got this plus, and then the rest, this part is the same as this part, and this part is the same as this part. I didn't change anything. Now, for the z component, you see there is this part and this part, which is the same, right? So let's imagine we factor it out. Then what happens is this. We have cosine squared v plus sine squared v. These gave us 1. So then we're left with this yellow part over here. And the rest I didn't change, I copied it exactly. Next, what I did is I factored out 4 times sine u. So I took sine u and 4, and I factored it out. So this 4 and this square is gone. That's why this is missing. Those factors, and same thing here. And everything else stays the same. I just factored out this. I did this just to simplify it a little bit so I don't have to carry around this factor for all 3 terms. Okay, so this was Tu cross Tv. Now let's get the expression for the vector field on the surface that we're interested in finding flux. This here, I copied the parameterization for the surface, and here I copied the expression for the vector field just at a generic point in space. So we want it on the surface and in terms of u and v, so we plug in x for the variable x in the vector field. This is what I get over here and over here. Then I plug in y here. So this is what I get here. Then for z, I plug it in here. And this is the expression for f. Now, one thing I forgot to do, so let's do it right now, is the bounds on u and v when I was parameterizing the surface. So let's do that. This was over here where I wrote the parameterization. Let's add the bounds. Here's how I'm going to reason this. We know that for a sphere, let's say a sphere of radius 1 would have parameters, let's say u, which really means phi, going from 0 to pi. So it goes from here to here. And then we have theta, which we denote as v, going from 0 to 2 pi. So this would go a full circle around. Now this is for a sphere of radius 1. But this is not quite what we're working with. We're working with an ellipsoid. Remember, it's stretched along x, y, and z by different amounts. But these parameters are the same. So you could imagine that we would map out the sphere, and then for every point on this sphere, there would be a corresponding point on this stretched out ellipsoid. Let me actually draw it to scale. Okay, so z is the longest one, y is slightly smaller, and x is even smaller. So we get small x, slightly bigger y, really big z, something like this. Yes, okay. But these guys stays the same. So, so we can just reuse this for this problem. Okay. So let's remember that u between 0 and pi and v between 0 and 2 pi. Okay, so let's use these bounds here. And what I have here is the expression for the flux integral. You see this f dotted with the differential surface element that has direction. Okay, so the bounds on u were 0 to pi, bounds on v were 0 to 2 pi. This expression over here, I'm simplifying it below. Here I copied the expression I had for f. I didn't change anything. I believe, yes, it's the same. Okay, this part is tu cross, sorry, including the 4 sine u, is tu cross tv that I calculated over here. The only difference is that I dropped the x hat, y hat, z hat, and instead I wrote this triangular notation. Yes, so let's simplify things. Next thing I did is I took the 2 and I factored it out of f and I merged it with this 4. That's how I got 8 sine u. And then the rest is the expanded dot product. So from this and this and this, I got this, this, and this. From this and this, I got this and this. And then for the z component, I had this and this. And I got and I got this and this with a minus. And then 8 sine u is the same, okay? And then next thing I did is I expanded. You see this product? I expanded it. Here's what I did. I took a product of square root of 3 and square root of 6. We know that square root of 6 is 3 times 2, square root of 3 times 2, so then I got 3 root 2. This is what I have here. And then this, the rest of this term, the way I got it is I took this sine u, I wrote it here, then this cosine u I got from here, and this cosine v I wrote here. The next term over here, what I did is I took this, so for root 2 times root 6, I have root 2 root 6 equals to root 2 times 3. That's how I got 2 root 3. That's how I got this. So then this term here is, sorry, okay, so then I have sine u, this gives me sine squared u, I have sine v, this is what I have here, and then I have cosine v, and that's what I wrote here. Then I have this term. This is what I have here. Let me just put a little arrow. Root 3, then sine squared u from this and this. Then I have sine v. This is from here. And then I have cosine v over here. Then I have minus and this last term. So I have square root of 2 sine u, cosine u, and cosine v. That's what I wrote here. 8 sine u stays the same. In the next step, I simplified some more things. For example, this term and this term are the same. So then we have 3 here and we have, well, just -1 here. That's how I got this. So we have square root of 2 sine u, cosine v, and then this 2 here. These two terms are also like terms. So I have square root of 3 sine squared u sine v cos v, and then the same thing here. And then we have -2 plus 1, right? So we just get -1. And we get the same term as above. This is how I got this part. Now you'll notice that this term that was here just now, it changed. That's because I made a mistake here originally. I replaced the wrong term. So what I did here is I used a double angle formula to replace sine v cosine v with sine of 2v divided by 2, and everything else hopefully stayed the same unless I made more mistakes. Now let's actually integrate. Oh, also this wasn't there. I forgot it. Now it's here. Yeah, so let's integrate everything. Here I just plugged in the expression for f dotted with tu cross tv. This is now here. The only thing that depends on v in this integral, because remember, first integration is over v, is this cosine v and this unfortunate fraction that keeps getting all the mistakes. Okay, now and everything else as far as v is concerned is just a constant. Now cosine v, when you integrate it over v from 0 to 2 pi, you get 0. And then the same thing for this one. 0 to 2 pi sine of 2v equals to cosine 2v with a negative divided by 2, right? Because 2 will come out and cosine will become negative sine, killing this negative. 0 to 2 pi. So this is 1 over 2 with a negative. And then we have cosine of 4 pi minus cosine of 0, which are really the same number, equal to 1. So then these two things cancel. So then you see integration over v gave us 0. This means that overall integration will just be 0. Okay, now let's move on to the right-hand side of the divergence theorem. Because remember what we're actually trying to do. We have this left-hand side of divergence theorem, which we found was 0, this flux integral. Now we want to find the right-hand side, the volume integral of divergence of f, and show that it's the same, so also 0. So let's do this. Here I copied the expression for f. This is the right-hand side. Then this is the del operator dotted with the vector field f. Then I'm expanding the dot product. So this differentiated with respect to x, you see this would give you 0. Derivative with respect to y of x also gives us 0. And derivative with respect to z of negative x also gives us 0. So we're integrating 0 over the region D. That's how we get 0. So the answer for the left and right-hand sides is the same. This is problem 15 from reading assignment 4, section 4.2.1. The problem gives you a vector field, y squared, negative z squared, and x. It gives you a circle in this parameterized form. So you have the position vector as a function of t is 3 cosine t, 4 cosine t, 5 sine t, with t going between 0 and 2 pi. And then the question says, find the contour integral of this vector field over the circle C using the Stokes theorem. So the question is actually very specific on how you're supposed to find this integral. Now, in this question, it's actually, it's probably possible to evaluate the integral directly, though I haven't tried doing that. But the question says to use the Stokes theorem, which means that you shouldn't be evaluating it directly, and you should be using the right-hand side of the Stokes theorem. Okay, so let's do this. What does the Stokes theorem say? It says that the contour integral we're looking for is equal to the integral of the curl of f over a surface S enclosed by the contour. Now there is a direction convention that's very important. So we have a contour C like this. You would imagine aligning your fingers with the direction of the contour. And if you do that, then your thumb will be pointing in the direction of the surface S. So surface S is oriented according to the right-hand rule. So all of these are right-hand thumb and right-hand fingers. And this is the surface S. Now, there is actually infinitely many surfaces that can be enclosed by contour C that are oriented like this. But generally, you should be using the surface that's the most convenient for you. So we want to use now the right-hand side of the Stokes theorem to get the value of this integral. First, let's compute the curl of the vector field f. Again, I have the del operator here, and then here I have the vector field. The x component of this curl is equal to 0 minus negative 2z. For the y component, I already put the negative, so we get plus 1 minus 0. For the z component, we have this determinant, so we get 0 minus 2y. And here I just simplified this expression. I got 2z because negatives canceled. And then I have -1 for the y component and -2y for the z component. Now let's describe the surface that we would want to select. This contour C was given to be a circle, and it lies on an intersection of this sphere and this plane. Now, you could probably select some other sort of shapes. These were the ones that came to mind. The reason why this left one is because, is because if I were to plug in this expression for x, y, and z, I get 25. Let me demonstrate. For x squared, I get 9 cosine squared t. Then I get plus y squared, so I have 16 cosine squared t plus 25 sine squared t. This is equal to, these two terms give me 25 cosine squared t, and then I get plus 25 sine squared t, and this is equal to 25. So you see, this is correct. How about this one? Well, this one I got by looking at the x and y coordinates. So x over 3 is cosine t, y over 3 is also, y over 4 is cosine t, so the two are equal. That's how I got this. When I plot, I used GeoGebra to plot this. This would be the sphere, and this would be the plane. And then the circle that lies on the intersection is exactly the contour C, right? So this is how it looks. Actually, it's not that crooked. One second. I want to make it straight, actually, because it passes through, like, it doesn't look the way I drew. It's supposed to pass through here. And then we have this dot. It doesn't look like a circle. Okay, this is going to have to do. Okay, so this is our contour C. Now we don't actually know which way it's oriented, so let's figure it out. Let's say when t equals to 0, this and this are positive numbers, right? So this would be 3 and this would be 4. And then the z coordinate is going to flip from a negative value to a positive value, right? Because t, when it goes from negative to positive, this guy flips the sign. So we have somewhere at this point, when x and y are positive, our z goes from negative to positive. So then the contour is oriented this way. So this means that the surface, which let's say we choose this flat surface like this, the surface should be oriented consistently by the right-hand rule. So this would be the direction. Let's parameterize this surface. My first attempt was actually different. I tried to parameterize the sort of how I would parameterize this a circle, but with, you know, like the distance from the center and some sort of an angle. But then maybe it's easier to just parameterize it in terms of x and z. So you could write u and v. I like to write out what those variables actually mean. So it's just parameterization in terms of x. X would just be equal to x. y would be equal to 4x over 3, I got this by rearranging this one, because then y equals 4x over 3. I've mentioned this before, but I'll emphasize. So this surface S is part of this plane. That's why I'm using this equation to describe y in terms of x. And then z is just equal to z. So now we have everything in terms of x and z. The bounds for x would be between -3 and 3. The reason I say this is because when I look here, when t varies from 0 to 2 pi, this x changes positive and negative, and it goes between -3 and 3. Now let's get the bounds for z. Now you'll notice this stuff here just changed because I actually had a mistake there. Now hopefully it's fixed. So when you vary x, you're sort of changing, where you are on this plane in this direction. And then for every one of those x's, you need to figure out how the bounds on z will go. And you see that those endpoints on the z are determined, all those endpoints, they lie on this sphere, right? So then we could use the equation for the sphere to solve for the z at those 2 points. So here, to get z, you will do z equals to plus or minus square root of 25 minus x squared minus y squared, right? So that's how I got these bounds over here. And then the next thing you want to do is you want to get rid of y, because we are going to integrate in terms of x and z, right? So then I plugged in this for y, and that's how I got here. Here I've just copied everything I wrote on the previous page, which is the parameterization of the surface and the bounds on x and z. Now let's find Tx, Tz, and their cross product. Tx you get by differentiating the this position vector on the surface given by x, y, and z with respect to x. So here, for this guy, you would get 1. Here you would get 4/3, and here you would get 0. This is what I wrote here, 1, 4/3, and 0. For Tz, I got 0, 0, 1, because this differentiated with respect to z gives you 0. Same thing here, and then here you get 1. Then for the cross product, let's compute what this is. Here I copied Tx, here I copied Tz. The result would be like this. You would have this determinant for the x component. This gives you 4/3 minus 0. For the y component, you would have this minus here. Then you get this determinant. So you get 1 minus 0. And then for the z component, you have this determinant. So you get 0 minus 0. Then in the end, I wrote it using this triangular notation, 4/3, -1, and 0. Now you should always check, once you did this calculation, that the way normal vector ends up oriented is what you want it to be. So in this case, Tx cross Tz, which is in the same direction as the normal vector to the surface, ends up in the direction of, it has a positive x component, so it's going to be oriented, like shown in this picture, as opposed to being oriented this way, right? So this is what I'm drawing is negative and hat, and we ended up with a vector that's oriented in this direction, right? Is this correct? Yes, it's correct, because this n hat that's shown here was obtained by using right-hand rule to get the orientation of the surface S. So you would align your fingers with contour C and your thumb points in this direction. And this is how you always should be applying Stokes' theorem. You should always make sure that your contour and your surface S are consistent by the right-hand rule in terms of orientation. Okay, so in this case, we're lucky. Our orientation vector for the surface was correct. But what happens if this is in the wrong direction? If instead of this guy, we got negative of this. So actually, we would get this guy. What you can do is you can just swap x and z. So then your z would be sort of your first variable and x would be your second variable. The result would be the flux that has the opposite sign. But now we don't need to do this. We just take tx cross tz. The next step is to write sort of this integrand, which is supposed to be curl of f on the surface in terms of parameterization variables x and z. This I copied from what we had before. I'll just show you where we had the calculation. The calculation was right here. You see, this is where we computed this, and then here I just copied it. And then I wrote it in terms of this triangular notation. And then you see there is this y right here. We don't like that. We want it in terms of x and z. So we use our parameterization right here to plug it into, so 4x over 3, and then we plug it into y. So y equals 4x over 3, and this is what I wrote here. Next step is to integrate the right-hand side of the Stokes theorem. You see what I wrote here is the flux integral. Here we have our differential surface element that has associated direction with it. The bounds I got from here. You see this yellow bound is over here. Let me highlight it. This is the bound on x from -3 to 3. And then this green bound that I shown you before, I copied it over here. And then here we have our curl of f. And you notice the videos in the previous portion of the video, it had said f, but the correct version should say curl of f. Okay, then I plugged in curl of f. So from here, I plugged it into here. I got this. Then tx cross tz, which is shown right here for third, -1 and 0. I plugged it in right here for third, -1 and 0. Then I expand this dot product. These two components give me 8z over 3 right here. -1 times -1 gives me 1, sorry. And then these two components give me 0 because of this 0 over here. Next, I realized that this function is an odd function of z. Remember, we're integrating first over z. So odd function of z. And this interval is symmetric around z. You see it goes from negative something to positive that same something, right? So this is symmetric interval. So when you integrate, this term will integrate to 0. because this is what happens when we integrate an odd function over a symmetric interval like this. Integrates to 0, because from z equals 0 to this number will give us a positive quantity, and then from negative this to 0 will give us negative quantity. Okay, here I removed this term I just crossed out. Next thing I did is I simplified this expression. How I did this is I noticed this is x squared and this is as well as x squared, and then I just did this calculation, 1 plus, so like 1 next to this x squared, plus 4 squared over 3 squared gave me 1 plus 16 over 9, which gave me 9 plus 16 over 9. So this is 25 over 9, which is what I have right here. And the same thing for the bottom limit. Then I factored out 25, and after square rooting, this gave me 5 here. Then I integrated over z, and I got this. So you see this, this guy will give me this, basically with 5, and this negative will make it 10. The next thing I did is I used trig substitution. How I used it, let me show you. A nice substitution for this kind of square roots is using sign, and I sort of want to kill this 9 with this 3. Another way I like to think about it is I like to imagine this as a side of a triangle. So I multiply this top and bottom of this guy by 9, and that's how I get the following. So 1 minus x squared over 9, when I multiply it by 9 and divide by 9, I would write one of the 9s here and one of the 9s like this. I would get 1 over 9, and then this 9 would go here, and I'll get this. So this is how I got this guy over here, and this 1 over 9 after square rooting became 1 over 3, so it's shown right here. So then after I did this, here's what I'm going to do. I imagine this being sort of like a circle with radius 3. So this is some hypothetical circle of radius 3. And my x is going to be sort of this vertical coordinate. And my u is going to be this angle. The reason I want to imagine it this way is because 9 minus x squared square rooted is going to be 3 cosine u. So it's much nicer than this, scary square root. And my x is equal to 3 sine u, which is, by the way, why I chose this u substitution like this. You can think of it just purely algebraically and just substitute it. If you see how this will simplify, then just go ahead, and you don't need to really draw anything. You can just go ahead. But I like to think of it geometrically. Okay, so this is the substitution. Dx is equal to 3 cosine u du. This is how I got this guy. This is my dx. This 3 cosine u is what I got from here, as I just discussed here, because this guy is equal to square root of 9 minus x squared just by looking at this triangle. And then the limits on u would be like this. X goes between -3 and 3. What does it mean? It means that my x equals 3 is here. Why? Because, well, that's when the vertical coordinate is 3, and this corresponds to u equal to pi over 2, and x is equal to -3 when the point is over here, and this is u equals negative pi over 2. So these are the bounds on u. Okay, so this is this integral. Now let's evaluate it. This 3 cancels, and we're left with this 3 times this 10. That's how I got the 30. I have cosine u times cosine u, cosine squared u. Then I used the fact, I did two things over here. First, I used the fact that this interval is symmetric and this function is even. So I can write the integral, I can just half the interval of integration and put this 2 over here, right? Second thing I did is I used double angle formula to rewrite cosine squared u like this. The reason why is because all of this is easy to integrate. So then I canceled this 2. I wrote 30 outside of this integral, and I just went ahead and integrated this part I'm showing you here. So this would be u plus 1/2 sine of 2u. And then the bounds are 0 to pi over 2. And then integrating this, I get 30 times pi over 2. And then this guy, when I plug in pi over 2, it becomes 0. And when I plug in 0, this guy becomes 0. So this guy is gone. And then we simplify and we get 15 pi. And this is the right-hand side of the Stokes theorem, which is equal to the left-hand side. So this is the circulation we were looking for.